Hi everyone, my name is Matt and I'm an application chemist at Nanalysis. Thank you for joining me today for my discussion on the analysis of lignins using 31P Benchtop NMR Spectroscopy. For those of you unfamiliar with our company, Nanalysis manufactures Benchtop NMR spectrometers, and we've been a pioneering force in this area for over 10 years. I'm very excited to be sharing some of our recent developments with you, so let's get into it. The history of NMR is very much a history of innovation. From the discovery of the electron's spin and magnetic moment, through Bloch and Purcell's fundamental discoveries, the old Varian spectrometers a few of you might remember, to the pioneering work of Bruker, who released their 500 megahertz spectrometer in the late 70s, then their 1000 megahertz spectrometer approximately 30 years later, the field of nuclear magnetic resonance has never stopped evolving. Finally, since 2010, we've seen the introduction and proliferation of benchtop NMR technology, which has been helping address some of the major accessibility concerns pertaining to the incorporation of traditional high-field spectrometers into many laboratories. To clarify, I'm not saying that benchtop NMR instruments are poised to replace traditional high-field instruments, but rather that they have helped increase the areas in which NMR can be used, allowing more and more people, experts and beginners alike, to learn about this technique and apply it to their individual workflows. The miniaturization of benchtop NMR technology by Nanalysis was done by 1. Using rare earth permanent magnets, specifically neodymium iron boron, and arranging them in a highly homogeneous and compact array, which allows us to use minimal amounts of magnetic materials and to have very limited stray fields, meaning the instruments are safe to be around. The instruments have very little current draws, and standard power can be used to power them. They don't require cryogens or significant maintenance, and non-experts can easily use them. Second, the miniaturization of electronics means that we've been able to condense these down from the large electronics boxes of traditional high-field spectrometers into small circuit board stacks and embed a computer for direct processing if desired. Alternatively, a separate computer can be used to control the instrument. Nanalysis currently offers two main product lines, the 60 MHz and 100 MHz instruments. As I mentioned on the previous slide, they're based on neodymium iron boron magnets and have very limited stray fields. We have a 1H only model for customers doing routine analyses, as well as some more complex heteronuclear experiments available to users hoping to collect additional data from our instruments. All the data I'll be presenting today was collected on our 60 Pro instrument line. Now that you know a little bit more about the instruments we offer, I'd like to sort of situate them within the context of current technologies. When we think of traditional high-field spectrometers, we know they offer incredible resolution and sensitivity, but they have low accessibility, and it's often not feasible for labs to incorporate these instruments into their workflows, whether it be due to their price, size, or need for expert staff to maintain and use them. At the other end of the spectrum, we have low field and low resolution relaxometers, which are less expensive but can only be used for relatively basic applications. We like to think of benchtop NMR technology as bridging the gap between these two, by addressing the accessibility issues inherent to high-field instruments while still providing high-resolution analyses. There are many underserved markets that could take advantage of the strengths of NMR as a technique, but the combination of price, size requirements, and expert staff for maintenance is simply too much for many people to handle, meaning that NMR tends to fly under the radar, no matter how powerful of a technique it is. Switching gears, I'd like to very quickly go over some of the key concepts relevant to quantitative NMR, or QNMR. One of the beautiful things about NMR is that it's inherently quantitative, meaning that the integration area of each individual signal is directly proportional to the number of chemically equivalent nuclei giving rise to that signal. This is important because it means that a specific analytical standard of the target analyte is not required. When we think about HPLC, for example, if you're targeting something like tadalafil, then you need a specific certified tadalafil reference standard to quantify this analyte. Your instrument needs to be calibrated, and careful consideration must be taken to properly separate all components during a chromatographic run. With NMR, we don't need to separate the components of interest like we do in chromatography, which enables us to obtain a snapshot of everything in solution. Additionally, a single resonance can be used to quantify the molecule of interest. I've taken an example from one of our published application notes on the right, where, without going into too much detail, we were able to quantify tadalafil using the peak represented by the green circle and using DMT as an internal calibrant, represented by the red circle. In other words, we used DMT, a compound with a known purity, to determine the purity of tadalafil. Tadalafil gives rise to a complex proton spectrum, with most of the signals overlapping significantly, making it nearly impossible to integrate these accurately. However, since we only need a single resonance to quantify the whole molecule, we were able to use the one shown here to obtain great results. Importantly, the analysis is also non-destructive, meaning that valuable samples can easily be recovered after analysis. There are a few main calibrant methods used for QNMR, such as using internal or external calibrants, calibration curves, or even a digital approach called arretic. I'll focus on the approach I'll be using in my talk today, notably the internal calibrant method, which is the one shown here on the right for tadalafil. An internal calibrant will typically be weighed directly in the same vial as the analyte of interest, and both will be dissolved together and transferred to an NMR tube. For this to be successful, the internal calibrant of choice needs to be of high purity, and this purity must be known. For example, Sigma offers a line of trace cert NMR calibrants, which are provided with very accurate purity values. Additionally, the signal of the internal calibrant cannot overlap with other signals in the spectrum. It must be completely soluble in the medium of analysis, and it must not react with anything else in solution. Using the general equation shown below, purities and quantities can be readily determined using this approach. This is an extremely powerful technique, and one that's been rapidly gaining in popularity over the last several years. As I mentioned, QNMR is rapidly gaining in popularity, but as more people start to use this method, it's important to realize that there are a few key things to consider when preparing for a QNMR analysis. It's extremely important to be accurate at every step of the way, which means using proper weighing techniques to minimize error. In fact, this is one of the most common sources of error in QNMR. Additionally, proper liquid dispensing methods must be used, which means proper use of a volumetric flask or a calibrated micropipette. It's crucial that acquisition parameters be optimized for collecting QNMR data. Simplified, this means that an adequate number of points must be used to sample the data, and the repetition time and spectral width must be carefully chosen to enable optimal results. This cannot be overstated. Typical acquisition parameters used to collect traditional one-dimensional NMR data will almost never provide accurate, quantitative results. Related to the acquisition parameters, scan delays must be chosen such that all spins of interest are fully relaxed between pulses. This is necessary to obtain accurate integrations, which form the basis of QNMR. This is achieved by determining the T1 values of the signals of interest and selecting a scan delay of approximately 5 to 7 times the longest T1, typically. Even though the scan delay is technically an acquisition parameter, I've given this its own section because of how important it is. You cannot collect accurate quantitative data without first selecting the appropriate scan delay. I would now like to discuss heteronuclear NMR very briefly, because while I'm sure all of you have seen carbon-13 experiments, and probably also some fluorine-19 and phosphorus-31 experiments, it's possible that some of the key advantages of heteronuclear NMR have not been presented to you. While proton remains by far the most popular nuclide for NMR, it unfortunately has a very narrow chemical shift window, which means that overlap can be, and very often is, problematic, even on high-field instruments. Most of those familiar with just basic NMR knowledge will be familiar with how the most simple aromatic functionalities can give rise to very complex, often second-order NMR spectra. Heteronuclides, however, typically have much larger chemical shift ranges, which you can see on the right for lithium-7, fluorine-19, and phosphorus-31, as compared to proton. This leads to less overlap even at lower fields, and allows us to differentiate signals that have extremely similar chemical environments. As a few examples of where heteronuclear NMR is commonly used, 19F is widely used in the pharmaceutical and polymer industries, while 31P is an exceptional handle for organometallic complexes and is also commonly used for the analysis of biomolecular samples, such as phospholipids. Often, heteronuclear NMR is used in conjunction with 1H NMR, but in certain situations, we can gather all the quantitative information we need from heteronuclear NMR alone. For this application, since we'll be focusing specifically on phosphorus, I've highlighted some key numbers in the table on the right. Benchtop NMR technology is thriving for many reasons, but I'd like to highlight method development, technological innovation, and application validation as key reasons why this field will continue to evolve. Today, I will focus on this last point, where I'll do my best to try and provide you with examples of how benchtop NMR can be used to address specific industry problems by providing market-driven analytical solutions. The work I'll discuss in my presentation today involves the identification and quantification of lignin substructures. For this, we'll be focusing on 31P NMR. However, since lignin doesn't contain any phosphorus, we'll have to incorporate it into the lignin framework somehow. I'll elaborate on this next. I don't think I'm going to surprise any of you when I say that it's abundantly clear that we need to see widespread use of renewable energy, and we need it soon. Within this complex framework of renewables, which has become saturated with plenty of buzzwords, one of them stands out for the purposes of this presentation: biofuels. Put simply, biofuels are any fuel derived from biomass, which is essentially any plant material or animal waste. Within this group, lignin emerges as a class of complex cross-linked phenolic polymers. It's a major component of lignocellulose and is currently made primarily as a byproduct of paper production. Unfortunately, most of the lignin produced around the world continues to be burned for energy production. I use the word unfortunately because one of the wonderful things about lignin is that the monomers which make up its complex structure are important building blocks, which we've historically obtained from petroleum feedstocks. As I just mentioned, lignin is a cross-linked phenolic polymer, and through the design of some very innovative catalysts over the last decade or two, we've been able to break down lignin into these fundamental building blocks. Sounds wonderful, right? Well, here's the issue. Determining the structure of lignin is challenging since it's very complex and it's different for every single lignin sample. The reason this is an issue is that it's very valuable to know the composition of a lignin before attempting to break it down into value-added chemicals. I'm showing a representative example of a generic lignin structure on the right to illustrate its complexity, but also to show you that the main skeleton making up the structure is formed of repeating units, mostly based on the three phenols shown below. In fact, the free radical polymerization of these units is what gives rise to most of the lignin structure. Even if you're only somewhat familiar with NMR, you'll likely take my word for it if I tell you that the proton and carbon spectra of lignin suffer from significant overlap. This is the case on both high field and low field instruments. If we can't use proton or carbon NMR to analyze lignin, at least not easily, and it doesn't really contain any other useful NMR active nuclei, how can we determine the composition of these polymers? Thankfully, chemists have derivatized lignin with a wide variety of heteronuclides, the most useful of which has emerged to be 31P. As an NMR handle, 31P is 100% naturally abundant. It has a very large chemical shift range, and it gives rise to sharp lines. So how do we introduce phosphorus into the lignin framework while also maintaining its integrity? Before proceeding, I'd like to mention that the lignin analysis I'll be discussing in this presentation was performed as part of a round-robin study to assess a test method described in a future CSA group standard, the CSA group being the Canadian Standards Association group. While I can't divulge the full details of the method quite yet, it's expected to be published in early February, and I've included some reference details below. Additionally, we've also just submitted our own manuscript summarizing these studies for peer review and are hoping to hear back soon. I would highly encourage those of you interested in lignin analysis to keep an eye out for both publications. Now, back to the introduction of phosphorus into the lignin framework. We can actually use a phosphorylation approach, where all of the OH groups in the polymer will be transformed according to the general reaction scheme below. Using TMDP as the phosphorylating agent, which is the dioxaphosphylane shown below, and cyclohexanol as the internal calibrant, we can identify and quantify all the different substructures which make up lignin. As a proof of concept, we've phosphorylated several representative model compounds to illustrate that these will give rise to signals within the 130 to 150 ppm chemical shift range. To clarify, this is well known, but we wanted to confirm these results on our own instrument. From top to bottom, we have examples showing an alkyl fragment, a guaiacyl fragment, a carboxylic acid fragment, another alkyl fragment, a basic phenyl fragment, a para-hydroxyphenyl fragment, and finally a syringyl fragment. I'd like to note the peak for the phosphorylated cyclohexanol around 145 ppm and the peak for the reaction product between TMDP and trace moisture, which we use as our internal chemical shift reference at 132.2 ppm. While the lignins are thoroughly dried and moisture is excluded as much as possible during these experiments, we almost always observe a little bit of this product. To further demonstrate this approach, we phosphorylated an actual lignin sample, a Kraft softwood lignin in this case, and analyzed it on both a benchtop and a high field instrument. While the high field spectrum is slightly better resolved in the aliphatic and carboxylic acid regions, realistically, these two spectra are very similar. I've demonstrated visually and numerically where the different functionalities arise in the 31P NMR spectrum. The regions have been accurately determined previously, and I encourage you to look up some of the references I've included below if you'd like to know more about these. The main difference between the hardwood or wheat lignins and the softwood lignins is whether we'll be identifying and quantifying 4O5' functionalities or syringeal functionalities. We analyzed two craft lignins, one softwood and one hardwood. The 31P spectra from our benchtop instruments are shown here. The red circles demonstrate one of the major differences between the two lignins. Importantly, we notice that the syringeal content in the hardwood lignin is much larger than in the softwood lignin, which is exactly what we would expect from numerous previous studies on exactly these types of polymers. In all cases, the integration area of the internal calibrant was normalized to 1. And the specific integration regions described on the previous slide are used to integrate all the specific substructures of interest. We next looked at an organosolv hardwood lignin and a soda lignin. Again, we noticed some major differences between the two, but primarily the fact that the carboxylic acid content is much higher in the soda lignin, which is again exactly what we would expect since the soda pulping process is known to produce these types of lignins. Additionally, you'll notice that the organosolv lignin has a much larger alkyl content in the region around 147 ppm. Having confirmed that we could analyze and integrate the various regions of interest in these 4 types of lignin, we opted to perform a thorough study to determine the performance of our method, especially as it compares to high field results. We prepared 3 samples for each type of lignin and analyzed them all on the benchtop instrument. After processing the spectra, we calculated the concentrations of each substructure in millimole per gram using the same generic QNMR equation I included in the introduction. I know there are a lot of numbers in this table, but the important thing to pay attention to is how small the deviations are across the different runs. When we ran these samples on a high field instrument, we also observed great agreement, which was very encouraging. This essentially means that we can accurately and reproducibly determine the composition of various lignins such that anyone working with these products can ascertain what the value of these products might be, so that we can use some of the great catalysts that have been developed to break down the most valuable lignins into their monomeric units, instead of obtaining these through petroleum feedstocks. While the benchtop approach does require additional scans compared to the high field experiments, it's very important to mention that many laboratories working in these industries don't have direct access to high field spectrometers. This, coupled with the fact that the phosphorylated lignins should be analyzed as soon as they're prepared due to eventual decomposition over time, demonstrates the utility of benchtop NMR technology to help underserved markets gain access to these types of analyses. Even though this lignin analysis is extremely promising and could provide value to many of those that produce lignin, it's simply not feasible when samples need to be sent out to a third party for analysis, where they can sometimes wait in a queue for hours or even days. In conclusion, we analyzed 4 lignins and quantified their respective substructures using 31P QNMR. We were able to do this by phosphorylating the lignin, transforming all of the OH groups into functionalities suitable for 31P NMR. This is important because we can't use proton or carbon NMR due to the extreme overlapping of resonances. The results from our 60 MHz instrument match those from high field instruments very closely, and we feel strongly about the fact that while this approach has shown incredible promise over the last several years and has been studied quite a bit, accessibility concerns have made it difficult for the pulp and paper industry to incorporate this method on a large scale. In addition, the low cost of experiments contributes to making the benchtop NMR approach an attractive path forward for this analysis. Our vision is truly one where it becomes possible to develop methods on high field instruments, like this one for the phosphorylated lignin analysis, and implement them at the benchtop level to help industries leverage the power of NMR without many of the requirements of the traditional systems. One of the key takeaway messages here is that benchtop NMR technology offers unparalleled access to this technique to industries that have historically not been able to afford and use traditional high field spectrometers. In this sense, the benchtop systems can really help address accessibility issues for the incorporation of NMR into underserved markets. I'd like to thank a few people, namely my colleagues at Nanalysis, Susie, Juan, and Paul. I would also like to thank our collaborators, Michael at FP Innovations and Ian at Canada's National Research Council, for their help in optimizing our benchtop lignin method, as well as Melanie at CSA Group for some insightful discussions about their upcoming published lignin analysis standard. I'd like to thank all of you for joining me today and for listening to me ramble on about the wonders of NMR. You're welcome to reach out to us at any time at sales@nanalysis.com. Have a great day.